Log on, tune in, find out. Another good idea from Cambridge.
Yann Ollivier today. He will speak about Discrete Ricci curvature with applications.
Okay, so thank you for being here, and well, it's my first time here, so I'm really impressed about the working conditions in this institute, and it's really nice. Well, I'd like to talk about discrete Ricci curvature, but before I'd like to give you my main motivation, which historically came from concentration of measure. So let me start with maybe one of the most important statements in probability. So imagine you are playing heads and tails with a coin. So you're tossing the coin n times. N is a large integer, and well, you want to look at the proportion of times that you get head or tail. So you have a function f from your set x of possible outcomes to the set of real numbers, and this is defined by f of x. So x is a sequence x1, x2, xn of symbols, h or t, and f of x is defined as the proportion of times that the symbol xi is equal to h, say. Now, all of you know that when n is large, this is very, very close to 1/2. Then, so the first informal statement is that f is almost always equal to 1/2, and the fluctuations are of order 1 over square root of n. So this is not very formal, but if you want to turn this into a formal statement, you're going to have to introduce mu, the uniform measure, the uniform probability measure, on your set x, and you're going to compute or bound the measure of the points where the error is bigger than 1 over square root of n. So you might even introduce a parameter t. So mu of the set of point x such that f of x minus 1/2 is bigger than t over square root of n. So this depends on the parameter t. And you know that actually the control of the probability of error has the shape of a Gaussian function. So this measure is smaller than 2 exponential minus t squared over some constant, which I don't remember, but probably works with 2. Okay, so that's one statement. And now there is a very different situation in which you have a very similar statement. So this was discovered by Paul Lévy. It's about the sphere Sn. So the unit sphere in Rn plus 1. And now you take one particular function, which is the projection from the sphere to, say, the vertical axis in Rn plus 1. And now the statement is that most of the mass of the sphere is concentrated around an equator. So if you project the mass to a real line, you'll get something like this, which is very concentrated around 0. And you have actually the same statement. Maybe the numerical constant is not the same, but I don't really care about that. except this time, of course, it's not 1/2, it's 0. The center of the function f is 0. Now, you might wonder if there is anything common between these two situations. So let's try to generalize the statements a little bit. Actually, what happens is that these statements are not only true for these particular choices of function f, but they are true for any, basically any function f that does not depend too much on a particular coordinate xi, either on the sphere or on the discrete cube. So actually I have exactly the same statement if in the case of the sphere I replace f with any function from the sphere to R that is 1 Lipschitz. So 1 Lipschitz, you need a metric. On R, you have the usual absolute value, and on the sphere, you have the geodesic distance. So the length, the distance between 2 points on the sphere is the length, the minimal length of a path that stays on the surface of the sphere. So it's the geodesic distance. And then, of course, now you might make a translation on f. So the value around which you compute the error is not 1/2 or 0, but now there exists a middle value or expected value m. Actually, you can take the expectation of f such that f is almost constant and equal to 1/n up to an error of 1/√n, and the shape of the error is Gaussian. Now, the same is true in the cube. So f from x to r, and the same statement will be true for any f which is 1 Lipschitz for a particular metric, and the metric will be, well, if you play heads and tails, each single outcome changes the proportion of heads and tails by 1/n at most. So this is the metric we are going to use for the metric. Defined by the distance between a sequence x and a sequence x prime is simply 1/n divided by the number of indices I such that xi is not equal to x prime I. So each index I has an influence of 1/n as in the proportion of heads and tails, and then you have the conclusion. There exists a value such that f is almost constant up to errors of 1/√n. Now, one of my goals was to find a common proof for these identical statements between those two spaces. And for that, I need to take one further generalization of the case of the sphere, a generalization which might point into an interesting direction to find the common feature. And so this generalization is due to Gromov. So it's the Gromov-Levy theorem. So you are able to replace the sphere, the n-dimensional sphere, with any n-dimensional manifold, Riemannian manifold. X with positive curvature. So positive meaning at least as positive as the sphere, Ricci curvature of X is at least equal to the Ricci curvature of the sphere. So I'm going to explain what is the Ricci curvature in a minute, but that might suggest that maybe the discrete cube X might have positive curvature in some sense, because it seems to be the relevant feature in the smooth domain for this kind of concentration theorem to hold. So, Riemannian manifold, if you're not familiar with that, just think about a hypersurface of dimension n in Rn+1 equipped with a geodesic path metric. So, okay, now if I use the upper blackboard, I have to move all the chalk down. Okay. So, what is Ricci curvature? So you're considering, say, a surface in three-dimensional space, and you want to define its curvature. What are you going to do? You are going to use the to consider small shapes in your surface and see how they differ between shapes drawn on the surface and shapes as they would be drawn in a Euclidean plane. So let's start with two very close points x and y lying on a surface. So this picture is going to be infinitesimal, so x and y are very close on the surface. So this is a tangent vector on the surface, and then it's almost Euclidean, but not quite. So now I am going to draw a rectangle and look at the error. In a rectangle, in principle, opposite sides have equal length. If you have curvature, if you're in a surface, it's not quite true. And so if I start with x and y, I draw a rectangle, and say the small sides of the rectangle lead to points x prime and y prime, and say that the two small sides have length epsilon. And the long side has length d, and you have right angles between x prime xy and right angle between y prime yx. Then the fourth side from x prime to y prime is not going to have length d. So d prime is going to differ from d by a second order term in epsilon, in the length of the small side. So let's define d prime equal d times 1 minus k over 2 epsilon square plus some error term, which is, say, big O of epsilon to the 3. And now this defines k, the curvature. K depends on what? K depends basically on x and y, of course, but I will take the parameter as follows. So k, it's taken at point x, and it depends on the choice of a tangent vector v, say unit tangent vector v, pointing from x to y, so a first direction, and another tangent vector w from x to x prime, giving a second direction. So now k depends on point x and on directions v and w. And this is called, it's not the Ricci curvature, it's called the sectional curvature. At x in the plane VW, and it's actually a theorem that depends only on the plane generated by V and W and not on V and W themselves. Now, this is sectional curvature. It's not the one I'm interested in. The one I'm interested in is, in a sense, weaker because it depends only on V and it's the average over W. So the Ricci curvature R Ricci or R at point X in direction V is going to be the average of Kx VW, and the average is taken over the direction W. And that is the Ricci curvature. So let us give another interpretation of this Ricci curvature. You start with a point X. Now I'm going to try and draw a three-dimensional picture. So I start with X. So I choose a direction V. I move a small distance d in that direction and I get a point Y. Now I choose another direction W and I move a small distance epsilon. I get points x prime and y prime. So distance d and epsilon. And now I want to know if on average over the second direction W the distance between x prime and y prime is bigger or smaller than the distance between x and y. So I look at all corresponding directions around x and around y, and I measure the distance, and on average the distance d prime is equal to d times 1 minus epsilon squared over 2. Oh, sorry, I forgot. There is a factor n in the definition. So n times, and here it's epsilon over 2n. That's for well, actually it depends on the textbooks, but the most common definition is with the factor n, Rx v. So the distance d prime between one point of the left sphere and one point of the right sphere and the corresponding point in the right sphere is going to be d times 1 minus epsilon squared over 2 times the Ricci curvature of v on average over the sphere. And this means that, plus the error term, of course, and this means that curvature, Ricci curvature, will be positive when it's possible to move a small ball to another small ball such that the distance, the traveling distance between these two balls is smaller than the distance between the centers. On the other hand, if you have negative curvature, you take two balls and you try to move one ball to the other ball, and then the distance, the traveling distance between the two balls is going to be bigger than the distance between the centers of the balls. And that's how you can tell if a space has positive or negative curvature. Of course, it might depend on the point, it might depend on a lot of things, but now you can use this idea in a discrete setting. So, now I'm going Bourbaki style, and I'm going to give some more formal definitions. So, X D is going to be a metric space and I'm going to assume it is Polish. So that's for regularity. I don't really want to write that, but you don't need a lot of regularity. Now, with just that, I could choose a number epsilon, a very small number, and use the balls of radius epsilon and try to apply this definition. I want to be slightly more general, and I want to allow my balls to have weights on them. So instead of balls, I'm going to use measures. But you have to imagine that those measures depend on a point x. So the general data I need is the following. For each point x in my space capital X, I'm going to use a probability measure that represents somehow a small ball centered at x. And I'm going to allow full choice of those probability measures. So let Bx be a probability measure on my set X depending on X. So the typical example if mu is a measure, a global measure on X, and epsilon is a scale parameter, my measure Bx is going to be mu restricted to the ball of radius epsilon centered at x, and I want to get a probability measure, so I have to normalize. So on the right I use spheres instead of balls, but that just changes the normalizing factor here you see in front of the curvature, so it's n plus 2 instead of n. It doesn't change much to switch between balls and spheres. And in a general setting, I like balls better because spheres might be empty in a metric space, whereas balls, I know I can find some points in them. So that will be the example. And now, the definition is going to be so now you know that in the standard case, Ricci curvature depends on a point x and a direction v, but here in a metric space I don't know what the direction it is, so I'm just going to keep the 2 points x and y instead. And well, x and y will have to be close, but we'll talk about that later. So now define curvature, the curvature kappa of x, y by the relation. You want the distance between the balls, so the distance between Bx and By to be equal to 1 minus kappa xy times the distance between x and y. And that's the definition of the curvature kappa. So you'll see that.
Excuse me, what is the distance? Is the Haldor distance?
No, I'm going to define that in a moment. Of course, I didn't define what the distance between bx and by is.
Because you can have many different distances if you
Yeah.
put one on the other one, or
Yeah.
if you take.
So I'm going to define which one I use.
Okay.
And you see on the picture above, you see that I use a distance between corresponding points. Actually, I chose the best way to move the left sphere to the right sphere, and the best way is just a translation, of course. And this realizes the minimum of the distance over which corresponding points have to travel. So what I'm going to use is transportation distance, so Wasserstein distance. So d bx by is the L1 Wasserstein distance. So it's defined as follows. If you have mu and mu prime probability measures in a metric space on metric space X, then the L1 Wasserstein distance is defined as the best way, so that's an infimum, over all the possible ways to measure mu to measure mu prime. And so how is this defined? So a way to move mu to mu prime is defined by coupling psi. So psi is a measure on x times x. So psi dx dy represents the amount of mass that travels from x to y. And of course you have constraints. And one of the constraints is that you should start with mu. So it means that if you integrate psi of dx dy over y, you should get mu of dx. And symmetrically, you should end up with mu prime. So integral of over x of psi dx dy equal mu of dy, mu prime of dy. And now you take the infimum of the average distance over which the points travel. So that's just dxy times psi of dx dy. So now you have.
These are the marginal, no?
Yeah,
Okay.
of course.
It's a fiber bundle.
Sorry?
It's a fiber bundle.
Not really.
I will show you after the talk.
Okay. So now you have a complete definition. You can say that curvature is positive if the transportation distance between small balls is smaller than the distance between the centers of the balls. And of course you have a choice of the balls, because actually the choice of bx as a probability measure depending on x, this is exactly the same as choosing a Markov chain on my space X. And depending on the way you choose the balls bx, you can get different values for the curvature. So for instance, if you are on the real line, you know that the curvature in a standard way is 0. But if you choose balls that somehow reflect a tendency to go towards the origin of Rn, such as if you choose actually bx that is related to a process, a random process, so that the associated Markov chain is a random process going back to the origin with high probability, then you're going to see some curvature emerge because of this tendency to go back to the origin. So you can introduce that way a curvature due to the measured part of Bx, and that's related to a theory by Bakri-Emery, and actually this definition is compatible with a notion of Bakri-Emery curvature for random processes on smooth spaces, but I'm not going to talk about that in detail. I want to point that this definition works for any space, including discrete spaces. So now it's all good to write some definitions, but the question is, can you do something useful with them? So I'm just going to give a list of possible applications. Or not possible actually, because we did them. So what can you do with this definition? Well, in geometry, one of the first consequences of having positive curvature is that you're bounded, is a compactness consequence of positive curvature. Here, it's more complicated than that because you need some uniformity on the measured part, because you can have something that have positive curvature because it so happens that the parts of X which lie at infinity have a very, very small measure, and so it's compactness in a measured sense. So compactness results when you have positive curvature, you have a host of functional inequalities. So for those of you who know about that, you have a spectral gap inequality and a kind of modified logarithmic Sobolev inequality. Actually, it's a modified logarithmic Sobolev inequality. Logarithm Sobolev inequality, because the standard way to modify it is not suitable for this setting for some reason. What else can you do? You have, as in Bakri-Emery theory, you have contraction of the heat semigroup. So this goes with the functional inequality. Heat equation. So you have a rate of contraction in Lipschitz norm. What else? So these are general consequences of positive curvature on a metric space. I forgot to mention. Of positive curvature. I started with concentration of measure, so that's one of the important things we get. Well, it's kind of a consequence of those inequalities, functional inequalities, but you can get refined versions. What else? So these are generalizations of known results. Now I'm going to talk about new results that this point of view allows to prove. So even for the original case of smooth manifolds, you can get new results by reinterpreting the curvature using this setting. And for instance, my student Laurent Vesser improved spectral gap inequalities, because the usual spectral gap inequality you get on a manifold depending on curvature depends on the infimum of the curvature. And my student was able to have a formula for the spectral gap of the heat equation that depends more on the average of the curvature. So curvature is allowed to be very, very close to zero at some points, to be very bad at some points, and if it's good at other points, there is some kind of compensation. And this result is kind of new. Another new result that we got with Aldéric Joulin of Toulouse University is concentration of measure, but not on the space itself, but for the empirical average of a random walk on the space. So you have a function and you want to know the average of the function of the space, and you use a Markov chain Monte Carlo technique. You build a Markov chain with the desired invariant measure, and you iterate the Markov chain, and you take the average over the trajectory, and you hope that somehow this average is close to the original, the exact average of the function. And we could prove that this procedure on a space of positive curvature has good properties, and good properties means you have concentration of measure over the value that you get at the end. So with high probability, you get always more or less the correct value. For Monte Carlo Markov chain procedures on spaces with positive curvature. And actually this includes some examples that are relevant to statistics. So maybe I tell a few words about this later. But for instance, when you want to get the internet at home, and typically it doesn't work, and you have to call a call center, and then they tell you, okay, you're no one is available to answer you now. You have an estimated waiting time of 5 minutes, and then half an hour later you're still waiting. This can be modelized by a system, a configuration system on the spaces of employees of the call centers and the space of people who try to call the call center. And it happens that this space, equipped with the correct probability, has positive curvature. And this was, so we can apply our results, and they happen to be the best known so far, and they answer a question that was open, that had been open for some time actually, on the qualitative rate of the errors. So when they tell you that you have to wait 5 minutes and you wait for half an hour, they have no excuse at all, because the computation works, the simulation works. So these are for the consequences, but now I would like to talk more about the original motivation, which was concentration of measure. And for that, I advertised the fact that I can give a common proof of concentration of measure on the cube and on the sphere, but for that I need to check that the cube does have positive Ricci curvature in this sense. So for the case of the sphere, well, I started with the definition of curvature in a manifold, and I tried to give a more abstract and discrete version. So I did everything so that in the original case I get the original curvature, so I'm not going to give more details about that. You only have to worry about the scaling constant here, but the scaling constant, you know what it is, and you get it right in the end, so that's not a big worry. Now back to the case of the cube. shouldn't have erased that. So x is 0, 1 to the n for some fixed n. And so the metric above, it's the graph metric on the hypercube. I'm going to make a bigger picture. So that's an n-dimensional cube. And let's decide that the length of each edge is L. So now I need to choose a measure, bx, and I make the simple possible choice. So I use the measure from the example. So I start with a global measure on x, mu, which in this case will be the uniform counting measure on the cube, and a scale parameter epsilon. When you're working in a graph, the best choice you have for a scale parameter is to use the length of an edge. So you just take bx, the uniform measure on the ball centered at x. So explicitly, that's bx of y equal bx of x prime equal 1 over n plus 1 if x prime equal x or x prime is adjacent to x and equals 0 otherwise. So I'm going to take a point x here. So here is bx. It charges all these points. Now I'm going to take another point y. And here's by in yellow. That's by and bx. And now I have to prove that the transportation distance, the Wasserstein distance between bx and by is smaller than the distance between x and y. And this is simple to see. What's the best way to move bx to by? Well, for most points, you only have to do a translation to the right. But you're lucky because 2 points don't have to move at all. The point x and the point y don't have to move at all. So now, what's the distance? And you can convince yourself that this is indeed the best way to move bx to by. So what's the distance between bx and by? So in dimension n, out of n plus 1 points, 2 points don't have to move at all. 2 over n plus 1 times 0 plus n minus 1 points over n plus 1 have to move by the same distance by one edge. So n minus 1 over n plus 1 times L. And this is equal to 1 minus 2 over n plus 1 times L. And L is the original distance between x and y. And so you see that according to the definition above, the curvature kappa is equal to 2 over n plus 1. So the discrete cube does have positive curvature according to this definition. And well, actually, I said I have the choice of bx. I could have started with another measure mu, such as a Poisson measure, and I would have defined Bx in a slightly different way, but still curvature would be positive, you'd get formula, so you have a lot of flexibility actually in what you want to do, but this is when your space X comes just with a matrix structure, this is the simplest choice you can make.
Why is it, when you've just done it when X and Y are adjacent?
Okay, so this is a very good question, because originally, for the case of manifolds, you know that curvature is a local invariant. So you don't want to be computing kappa of xy for x and y lying at the two far ends of your space X. And for that, you need a criterion. And so this is an exercise. So if your space is reasonable, then you'll only have to check kappa xy for closed pairs of points x and y, and then the positive, if curvature is positive for closed x and y, then it will propagate at all scales. And reasonable means what? It means that it's geodesic. So let's so it's a definition before the exercise. Let alpha positive number, space xd, a metric space, is alpha geodesic if for any x and y in X, you can move from X to Y by jumps of at most alpha, and this realizes the distance between X and Y. So there exists X equal X0, X1, Xn equal Y with the true properties that E xi plus 1 is at most alpha, and this path realizes the distance between x and y. The xy is the sum of the xi plus 1. Now the exercise is suppose that X, the space X is alpha geodesic, and kappa xy, you know you have a good bound on kappa xy. So kappa xy is at least kappa 0 for points that are at distance at most alpha. Then you have the same lower bound on curvature for all points x and y. And, well, that's basically the triangle inequality for the transportation distance. So it's very simple to prove, but it's really, really important in practice, because otherwise you could never check that spaces have positive curvature. Okay, so now maybe I'll give a theorem. So I started with concentration of measure. So what's the kind of theorem that you can prove? So suppose, well, you have a lower bound on curvature. So kappa xy is at least kappa 0, and kappa 0 is positive. you want to get concentration of measure, so the end of the theorem is the following. Then, for all f from x, for any numerical function on x that is 1 Lipschitz, you have a concentration phenomenon that is the measure of all the points x such that f of x minus the average of f is more than something, some parameter t. This measure is smaller than a Gaussian function 2 exponential minus t squared over 2d squared, to write it in a standard way. And of course, I have several things to define. I have to tell you what is d because it controls the size of the error. And I have to tell you what the measure mu, and mu defines the expectation. I have to tell you what the measure mu is. So I mentioned earlier that in the definition, if for each x in my space I have a measure bx, this defines a Markov chain. If curvature is positive, you can check that this Markov chain has a unique invariant measure and that convergence occurs exponentially fast. You can see it at step 1 because it's the definition. So at step 1, you start at a point x, you replace it with bx, with a point taken at random in bx. You do the same for another point y, and you see that already after one step, you can choose a correspondence between bx and by that reduces the distance. If you do it again, the distance will reduce by a factor 1 minus kappa at each time, and so you'll have exponential convergence to some invariant measure in transportation distance. So let mu be the unique invariant measure and now I have to define d. So d is a length. D depends on the size of the space, whereas kappa doesn't. And you would like several features on d. So if x is twice as big, d is going to be twice as big. So you'll have factor depending on the size. Actually, you'll have a factor depending on the size of the balls here. So it would be epsilon if B is defined as an exact ball, but if you have a Markov chain, it's going to be something else. You would like to have the fact that in the sphere there is an inverse relation between the radius and curvature. Curvature is 1 over r squared for a classical sphere. So you would have to keep this kind of dependency between the deviation error and the curvature. So you'd like to d squared to be proportional to 1 over k, kappa. And you would like to know how dimension affects the result. Because of course concentration of measure is something that happens when the number of independent parameters is large. So you would like the error to be of order 1 over square root of n, with n the number of parameters. So you would like something like that. And of course, so kappa, is kappa 0, it's the one in the assumption. And now I have to define sigma and n. So both will depend on a point x. So sigma will be basically the size of the step of the random walk. So it will be the quadratic average distance between 2 points in Dx. Sigma square of x is by definition 1/2 integral x prime, integral of x second, distance between x prime and x second, square times bx of dx prime dx of dx second. So you have x, you have dx, you take 2 points x prime prime, and typically on average the distance here is sigma x. Now what is n? It's defined in a sort of tautological way. It's going to be a local invariant as well. And it's based on the idea that if you're in a space of dimension n, you take the distance between 2 points and then you try to project this in dimension 1. Then when you project in dimension 1, distances are reduced by a factor of 1 over the square root of n. Of course, you might say that's the definition of concentration of measure, but here I'm going to do this locally. And locally, usually you know what's happening in your space. So nx is going to be a kind of local dimension for concentration of measure, or local dimension for the idea that if you have n parameters, the typical distance in dimension n is given by the Pythagoras theorem, and you have to add the squares of the contributions of each coordinate. So nx is going to be the same quantity on the numerator. So you take the average x prime x second d x prime x second square, and now you're going to divide by the best you can do if you project in dimension 1. So you divide by the supremum over phi from the support of the measure bx to r, to the real line, of the same quantity, the same distance computed in the real line. So the absolute value, phi of x prime minus phi of x second square. And the measure is the same for x prime and x second lying in the ball of radius, in the ball around x. So now usually this is something you can compute, and if you start with a manifold or a surface, for instance, then you get the usual dimension, maybe up to a small numerical constant like 1.1 or 1.2 or something. And
some Lipschitz condition.
Oh, f is 1 Lipschitz, of course. Phi is 1 Lipschitz. So, and if you are in a graph, well, locally a graph is an object of dimension 1, and so for a graph nx, like for the cube, nx it lies between 1 and 2, I think. Maybe between 1 and 1.1. I don't care much about numerical constants. So now you have dx squared, which is sigma x squared divided by kappa 0 nx. Of course, there is a compensation between sigma x squared and nx, but I write it that way because usually that's the quantities you can control independently. At least in the case of a Riemannian manifold, you know that sigma x squared is roughly epsilon square, and nx is the dimension of the manifold. So it makes sense to keep the separation that way. And now, d squared, d is the quadratic average of the x squared. So now you have a complete theorem, except it's not true, because in the discrete setting, you don't always have Gaussian concentration. Sometimes you have a small number of rare events, a number of rare events of very small probability individually, but in the end they add up in a discrete setting, and you can get tails that have a Poisson distribution, for instance. And you need to take that into account. So then let T max. So the relation that you have here is going to hold only if T is not too large, equal something, which I will write maybe later. And here you have a Gaussian control if T is smaller than T max, and mu, and an exponential control, exponential minus, say, T max over 2d squared if T is above T max. So it begins like a Gaussian and it ends like an exponential, and of course it's only interesting if T max is big enough. And you can write a formula for T max. So maybe it's oh sorry, I don't get optimal constant here, so I lose something in the process. So the constant is really not optimal. It's 6 instead of 2 or something like that. And T max is given, well, maybe it's not that interesting, but it's d squared divided by d max. Okay, no, I'm not going to write the definition of T max, but depends on dx. And the important point is you can write a formula, you can check it explicitly, and for instance for the discrete cube, T max is going to be equal to the diameter of the cube, so you never see T max, you're always below T max. And even better, for a manifold, T max is going to behave like typically the inverse of the diameter of Bx, and so in a manifold you take Bx to be a ball of radius epsilon, and then you take epsilon tends to 0 and T max tends to infinity. So in the case of manifolds, you don't have T max at all. So that's how you recover a Gaussian concentration in the case of the cube or Riemannian manifold. And I think I stop here. Thank you.
Are there any other questions?
So is it? So you said, and I think I understand that. So if the curvature is positive, then the Markov chain is recurrent, positive recurrent. You've got an invariant measure.
Mm-hmm.
So I guess the question is kind of is this if and only if. So in particular, if the curvature is strictly negative, do you get into a situation where the walk has a speed maybe or something like that?
If curvature is negative, the random walk cannot escape too fast, but it's an exponential control. Like, well, there is a complete equivalence between having curvature at least kappa and having contraction by a factor 1 minus kappa in Wasserstein distance by the random walk. So if 1 minus kappa is negative, that means that you can explode, but then the statement is still meaningful, but it's not very interesting.
Your definition of kappa is the relationship between the distance from ball 2 points. Now, if you change the balls, you change kappa.
Yeah, sure. So,
And, but you never say something related with the problem that you can have more kappa depending about what kind of set you take into account.
yeah. So maybe a good example for this is what happens on a real line. So x equal r, and if you choose the naive way to choose the ball, so if you take dx uniform on a ball of radius epsilon on the interval x minus epsilon over 2, x plus epsilon over 2, then it's pretty clear that it's translation invariant, so you get kappa equals 0. Now, as I said, there is an existing theory of how on the real line you can have random processes which, in the sense of Bakri and Emery, have positive curvature. For example, if you take a random walk whose invariant measure is a Gaussian, then you expect curvature to be positive. So typically the random walk that leads to a positive curvature is the following one. You take a so-called Einstein-Uhlenbeck process. You take, it's a continuous time thing. So consider the SVE x t plus delta t. So people in stochastic differential equations will probably kill me because of that notation, but doesn't matter. Equal xt minus delta t times xt plus square root of 2 delta t times a noise term. That's how you simulate a stochastic differential equation on a computer. So that's discretization with time step delta t of the Einstein-Uhlenbeck process. So you have a noise term. If I remove the middle part, you have Brownian motion on the real line. If I take the middle part into account, you see that at each step you move a little bit towards the origin. And that will create the curvature. So now, Bx is kind of uniform in x 1 minus delta t minus square root of 2 delta t, x 1 minus delta t plus square root of 2 delta t. So if delta t is chosen and delta t is chosen small, you see that this is a random walk which approximates the stochastic differential equation, and now Bx depends strongly on x, and it's not translation invariant anymore because it has an offset towards the origin. And now it's pretty clear, if you think about the picture, that curvature is going to be positive. And curvature is going to be equal to delta t. Because you are going to have something like that. 0 is here, x is here. Bx is going to be something like that. And if y is somewhere to the right, by is going to be something like that. And the distance from bx to by is going to be slightly smaller than the distance from x to y by a factor 1 minus delta t. And you can actually generalize this to any SDE, any stochastic differential equation on a manifold. So if you have an SDE given by a fourth term f, and you have a vector field f such that Px is centered at x plus f of x times delta t, say, with a noise term that jumps into a ball, and you start at another point. Now, what's going to happen? You're going to have to compute the transportation distance between Bx and By. So between corresponding points, you know that once you know the centers of the balls, you're in a Riemannian manifold, so you get the usual Ricci curvature if you start at the centers of the balls. But then there is an additional difference, because the distance between the centers of the balls is not the same as the distance between x and y. So you get two contributions to the curvature in this kind of situation. One is the contribution of curvature of the space of the ordinary curvature of the space you're in, and the second contribution is typically like the divergence of the vector field f or something like that, and you can write it explicitly. You can compute it with physicist arguments like when f is small and the distance from x to y tends to 0, what's the distance from x plus fx times epsilon and y plus f of y times epsilon, and you expand at first order, etc., and you get the Bakry-Emery curvature.
So, since it's a bit late, I suggest that additional questions be asked in private. And, thank Olivier again.